Okay, so now we're going to go to the next chapter, dealing with free processes, free. So we have spent a lot of time now with bound-bound line transitions. So we're going to spend today talking about free emission, or as it is called, Bremsstrahlung in German. Braking radiation. So obviously now we're dealing with not bound systems anymore, but free. So the essential picture that we will have is that of an ion. It's going to be a proton. We're going to use our normal hydrogen as an example. You could add more nuclei, and then you have to scale the resulting relation with the nuclear charge, C, just as we did for bound-bound transitions, for example, in the Bohr atom, right? And now you have an electron sweeping by that is not bound to the proton, okay? But it is coming by here, and when it is flying by, it is subject then, of course, to the Coulomb force. So there will be an attraction between here set by the Coulomb force. Again, we assume non-relativistic, so this Coulomb force then is just E squared divided by R squared. And what will happen then? Well, this electron will, of course, deviate a little bit from its path, like this. Okay? Now, I should say this sketch, even though I put it pretty modest, is very exaggerated even so, because the deviation here is typically tiny, tiny, tiny. But still, there is a measurable effect. Now, that is, of course, a change in direction, an acceleration. Yeah? And what do we know by accelerating charges? Well, they radiate. They radiate according to our familiar Larmour's law. Here is again a situation where it is reasonable for us to treat this classically. We will do a little correction at the end, as usual. Here is our Larmour's formula. So if we put this, the response here then is by emission of a continuous spectrum. Remember that when we had this in sort of, say, the bound-bound situation, and we treated it classically, we actually had a similar situation where we considered the spiraling in, and so to say, the death of classical physics by means of that. Now the electron is not bound, so it's a free system, but still it is affected, it deviates a little bit, and it emits radiation according to the Larmour formula that we have had. Okay, what is this acceleration? Well, this is just Newton 2, right, since it's classically, so we just have this ma there. And then, of course, we can just insert this immediately here to get to 2/3 e to the 6. We have c cubed, the mass squared. And then it's a question, what should we do for the radius here? So what we will assume now is that the action happens only when the electron is closest to the proton. And this is actually not such a bad approximation at all. That is, if it is far away like here, like so, then of course the radial distance between the proton and the electron is much, much greater than here. And then this becomes negligible as compared to here. So we're going to assume that all the action takes place in a very little interval here. We're going to approximate this R minimum distance with the impact parameter B. So we're just going to write that this is 1 over then B4. Okay, B being our impact parameter in this case. Now, furthermore, in this picture, we have assumed that the proton is at rest with respect to the electron, so that there is no relative motion. There is relative motion, but we can assume that it is at rest. And this is reasonable if we now assume that there is a thermal situation such that the temperature of the electrons is equal to the temperature of the protons. Okay? So if we have a thermal plasma, remember that our thermal speed, right, was defined as 2 kT divided by the mass of the particle. So, of course, now, if the electron and the proton speeds, temperatures are the same, then the V thermal of the electron will be much, much greater than the thermal speed of the protons, because the mass of the electrons are much smaller. So, the thermal electron much, much greater than the thermal proton. So, in a relative sense, it is okay for us to assume that the proton is there at rest. Okay, so then, of course, we're going to continue with the single proton here. Yeah, but we're not just having one electron that is just streaming by, but we have a flux of electrons, a swarm of free electrons coming into us like this. Now, we know what we mean by a flux in this case, so we can take the number density of the electrons times some characteristic speed, which will, for now will be constant, yeah, of that. Then we get the number flux of the electrons. And then they interact here, and then we can take at some impact parameter B, we're going to draw a perfect circle, and a little annulus here of dB, such that the area of this is 2 pi b, that's the circumference, times dB. Okay? And then the emitted energy here, right, will be, we know how to get to like an emission energy has to be the energy then of one of these times the number density times their velocity. Then we have an energy flux, yeah, the number flux times the energy of one of them becomes the energy flux, and the energy flux times the area 2 pi b dB times the area. Well, that we know that is our luminosity or our power from this whole swarm then. All of this we have done in different contexts before, right? So the energy there is another approximation because that's the energy of one of them now, right? So that's essentially the power and then the time integral, right? But we're going to approximate that this is just in a small distance here, right? So we're going to say that this is the power there times a little delta t times a little tau, which is the time now it takes, and that is then just p r divided, no, b divided by the velocity. That's again the same assumption that we're assuming that all actions happen within a very small integral here, so that we can just simplify this integral. Now we get for the of an ion, the power of one ion here is then just this one, 3 E6 divided by C3 cubed 1 over B4. We have this, B divided by V, and then we're going to have to integrate it by number flux times 2 pi B dB. Okay. Let's see. We have 2 of these, so that becomes a 2. The velocities cancel. We have a 2 pi there, so we have something like a 4 pi then, I guess. So this looks like 4 pi 3 E6 C cubed M squared, number density of electrons, dB divided by B squared. So that's then the p ion within this little annulus. So it's useful for us, instead of doing this now within an annulus, to consider the typical frequencies of radiation, which we can, since we're again in the limit. So if we again have the deviation, then the angular frequency times the radius, we know it's the velocity, right? Meaning that 2 pi times the frequency, if we prefer to work in our ordinary frequency space instead of angular frequency, is going to be the velocity divided by b. Okay? Where b is our impact parameter. Now, that then means that the new dB is going to be v 2 pi b squared, right? Or dB b squared is going to be the new 2 pi divided by v. So if we write this and we put it now, that the ion within a little frequency integral, well, the nu is going to be eight pi squared divided by 3 E6 C cubed M squared NE divided by the velocity the nu. Yeah? And here we actually already have a quite interesting result. And that is that the emitting power, or the emitted luminosity, is independent of the frequency band. Now, that has to do with this area and frequency dependence here. That is that if you have now flux of electrons coming in at a higher, at a larger impact parameter, right, at a larger B, so that you make this bigger, this annulus, so it's out here now, then what will happen? Well, the characteristic frequency of the radiation will be lower, right, because nu goes with 1 over B. But on the other hand, your area that you have at that annulus will be higher because the area, well, it is larger, right? So that has a compensating effect, making it that the total there is actually independent of the frequency band. So, and this is of course then for a given speed v that you're coming into. Now, of course, in reality, you're not coming in with a given speed like this, but you have a distribution of speeds. So really we should write this as a function of nu, but also as a function of v, velocity. Hope you can see the difference between the nu's and the v's. The nu. And then we're going to have to fold this, of course, with all the velocities. And here is again where we use our velocity distribution, which is, again, it's a thermal situation. So we assume the Maxwellian, which we have done before. Now I'm going to write it down, e to the minus mv squared divided by q dt. And then I'm going to have this one here, v squared dv. And that is because I'm interested now in the distribution of speeds. Previously, when we did this in the Doppler shift for the bound-bound processes, we were interested in the line of sight velocities. Here, we're just interested in the speed distribution. So this becomes, the folding here becomes a little bit different, okay? Now, all right, so if we now want the, say, averaged then emitted power in the nu, we have to then get this from some minimum velocity to infinity, p nu v, and then f of v, and we have to integrate over all the v's, and then we have the d nu there. All right? So now this minimum velocity here I've introduced, and technically, I mean, you could imagine, okay, we're going to integrate from 0, right? But of course, if the electrons don't move, v equals to 0, well, then there is nothing really happening, right? And, you know, they always move a little bit, but anyways. So this is essentially set by them delivering all their kinetic energies, yeah? And so you can't have energies, h nu, of the corresponding electromagnetic radiation that is emitted that is higher than the actual kinetic energy of the electrons. So this then sets a minimum velocity. Now, well, now we have a lovely integral again to solve. Seems like we've done this already in some context somewhere, but I don't know. What do we get? Well, we have some expression there, right, of 8 pi squared divided by 3 E6 c cubed m squared, the Ne, that's the number density of the electrons, right? And then we have the integral here, V min to infinity. We have 1 over V, and then we have 4 pi, We can, of course, take out those 4 pi's as well. And, oops, I'm going to take out some more stuff. I saw we had there as well, 4 pi, and we had this whole thingy here, KT 3/1/4. All of this can just be taken out, and then we can integrate from V min, and then we had 1 over V, so 1 V cancels, so it's V e to the minus mv squared divided by kt dv, okay. That's nice. While I take out this part of the blackboard, let's see if you can figure out, because it's very similar to a lot of other stuff we've done. They all seem to come out in this form in some way or another, huh? That's a joke, but you know, it's not uncommon. So the variable substitution that is good here is just x mv squared divided by 2kt, okay? Because then dx is just vm kt dv, right? Such that the, if we call this now j for integral, we have this as m divided by kt x min to infinity and whatnot, dv, yeah, that's what we wanted, right? So that's just e to the minus x dx, voila. This one we know how to do. We have probably up, it's just m kt e to minus x min. Sorry, sir, if I did a sign error. On the way. I don't think I did, actually. Now I took out everything, so you have to go back into your notes and plug it all back in. And then we're going to end up with a lovely expression for whatever it was that we were calculating, which was, I have it somewhere here, the average emitted power by 1 ion Bremsstrahlung classical limit under the approximation that we did. Yes? Sorry? Yeah. But I took you have to take the derivative, then the 2 comes down. The derivative, yeah, exactly. dv, v, you have 1v dv. This is just the derivative. And these 2 cancels. Yeah. Calculus A. We can fix that in the break. I know where the problem arises, right? Okay, so if you do the x dv of this, then m to kt, right? But then you have to take the derivative of that, and that's 2v. So it's just that. I just skipped that step. That is correct. Kt over m. Very good. Nice. All right. Back to that. If we plug it in and we manage to do somehow the algebra correct, yeah, we should get this expression out, which I did once back in the time. back in the days. So, now, here is our flux of our emitting power for Bremsstrahlung. Okay? Again, provided we manage to somehow do the algebra correctly, which this should be. So, in our course, though, we of course always want to put this in our radiative transfer language, right? So we're going to write this now as our emission coefficient, either nu, as we had, and then this is just the emitting power for one of it, right? Times, of course, the number density of the ions themselves, because this was now for a flux of electrons, right? But only for one ion, so we have to multiply it with the ions density themselves, okay? And then we have the average there. And then since we defined in our chapter 3, so we go back to that, this per steradian, so per solid angle, we divide by 4 pi. Now, this we can write, and I'm just going to write it now with the correct expression, the full expression, with numerical values inserted in CDS units. Okay? That is 5.4 times 10 to the minus 39 NE and I t to the minus 1/2, which you see from there, right? E to the minus h nu kt, and really this should of course be like this if we're going to be technically correct, because it's in the cos integral. And then we're going to multiply it by some factor GFF. Okay, and here is our either nu free or Bremsstrahlung emission coefficient in our their CDS unit, which we can use. Now, I'm going to make 2 points here. One, of course, is a little bit of an exercise to carry out this to this and to get the algebra correctly, right? Now, if you do this, you will get an expression which actually differs from the exact expression, which is numerical value here and which is expressed in the lecture notes with also symbols. From our calculation, that is different by a factor of 2.1 something, okay? So numerical factor in front. All the dependencies are the same, but the numerical factor in front is different. And that has to do with the assumptions that we made in the beginning here leading up. In particular, this little tacky integral I did, where I just said that, okay, it's in a very small interval here, so we approximate that just this is just B over V. Right? If you do this more carefully, then you get a small numerical factor. But to understand the process where this comes from, that is not, of course, the important thing here. The important thing is to understand this is what we can use, the correct expression that we use, and where does the Bremsstrahlung or free
emission in the thermal regime, as we're assuming here, actually arise from. How does it come about? It's the Maxwellian, it's the approximation of the deviation, the the deviation which caused the accelerating electron, which then together with the Larmor formula, because we have an accelerating electron, we know it's radiating a continuous spectrum, this is a continuous spectrum, and so forth. And then we're carrying it out the analysis. Now, there is another correction factor, GFF, and this is called the Gaunt factor. Now, that Gaunt factor is, in some sense, I guess, similar to the oscillator strength for bound-bound transitions. That is, you need to do some quantum mechanical corrections sometimes here. It's actually this classical here, without this, assuming this as just a unity, is actually, for most cases, not a bad approximation at all. But it has a small weak dependence there. And it has to do both when you come too close, right, to the atom, you start to experience quantum mechanical effects. And also it has to do with screening effects, actually, at higher radii. That, you know, you get screened by intervening electrons, okay? And both of those leads to small correction factors, which, again, we don't have to worry about here, but I wanted to mention for completeness. Huh? For our purposes in this course, we can assume that it's unity and it's going to be good enough, okay? It's actually good enough for a lot of analysis. All right. Well, let's move on here a little bit now. Here we have our emission coefficient. Let's see, what can we say about the absorption coefficient? Well, we know that eta nu, alpha nu then, is the source function, right? But this is a thermal process, so what's the source function for a thermal process? This we know, it's December now in the course, and we know this. Planck. The Planck function. This is B nu of T. Source function for thermal process is the Planck function. Yeah? So we can see directly, we can just write down that alpha nu is going to be eta nu divided by B nu. So that's just this dribble over there, which has some stuff in it, right? So it's a numerical fact. Okay, I'm just going to write it down. I was going to do proportionalities, but it's going to be as messy then. So. And then we divide by the Planck function, c squared. Okay, now if we do that proportionality, we see that we have NE, NI, right? And then this comes over there, so we have nu to the minus 3. Going to say proportionality there, not with that, because otherwise we get the same symbol as alpha. So that's my proportionality now. Nu to the minus 3, right, from there. But then we have this over here, which, of course, has to go up there. So then we're going to have 1 minus e to the minus h nu kt. So this is the expression, the proportionality, for the extinction coefficient. And of course, you can just plug in the numerical values to get the correct numerical value in here. I will give it to you. It's also given in the lecture notes, of course. Now, we will do one interesting thing already now, though, for the free extinction coefficient, absorption coefficient. And that is that, okay, so turns out that this is very often important in, for example, radio emission. Yeah? So
That is often from objects dominated by this Bremsstrahlung. Yeah? Now, radio emission is high wavelengths, so low frequencies, right? And remember what the process was. The process was a free-free where we had a charge in the middle and then free electrons. So we need to have those ionized atoms, right? Well, we have learned from our previous, in order to have an ionized situation in general, we need to have significant temperatures, right? So typically this is important in nebula, and that's the example that we will do, which is on the order of 10 to the 4 Kelvin. Okay, it's just one example where it's important, so-called ionized nebulae around typically clusters of young, hot, massive stars that ionize their surrounding in so-called H2 regions. Yeah, radio emission there dominated by this. But then, of course, if T is 10 to the 4 and we're interested in radio emission, then we see that H nu divided by KT is much, much smaller than 1. That is, that we're in the Rayleigh-Jeans tail. Okay? Now, in the Rayleigh-Jeans tail, you see that alpha nu, free then, changes behavior. I missed the temperature here somewhere. Yes. 1/2. But then, of course, this is just 1 minus that. This is the Taylor expansion we know by heart now. And then 1 nu comes out. So this is then, and 1 over t. So this becomes minus 3 halves and E and I nu to the minus 2. So that's the proportionality in the Rayleigh-Jeans part of the spectrum. So let's look at a simple, interesting example here now. We have our, I'm going to take this out and I'm going to rewrite it actually from my notes. I think that's the easiest way here. All right. So let's assume now we have a cloud, an interstellar gas cloud here with some temperature. We're going to say later that it's on the order of 10 to the 4 Kelvin. It doesn't have to be that, but it can be that, okay? And then we're here. We're going to observe this cloud now. And we're going to say it has a constant temperature and also constant density. It's a homogeneous cloud. We're going to further assume that the incoming radiation here is 0. That is, that it's not backlit. It's not lit from any sides. Okay? Right? But we know the transfer solution through a homogeneous cloud. Right? That's the homogeneous slab solution. So the emergence intensity here that reaches us will be I nu in e to the minus tau nu, where tau nu now is the optical depth of the cloud, right? Plus S nu, 1 minus e to the minus tau nu. S nu here, we could do the integral directly, take out S nu, because it was constant, remember? We also did this for other situations where we had a linear dependence on tau for the source function. That was the Eddington-Barbier and other situations, if we go back to our chapter 3. But this was the homogeneous slab solution. Now, of course, in this situation, this one was 0. We said it was not backlit. Furthermore, we have said that the emission here, we're going to assume, is from free or Bremsstrahlung. Okay? Now, if the emission here is from Bremsstrahlung, thermal Bremsstrahlung, then S nu, of course, is B nu, right? So then we see that the emergent intensity will just be B nu of this function T that we had, of this temperature that we assumed, e to the minus tau nu. Now, tau nu, we know is just alpha nu, and we have assumed that it's just free, yeah? And then dl, but we also said that it's homogeneous, so the density doesn't vary, the temperature doesn't vary. So then this is not a function of position in the cloud, which it generally is, of course. But then we can just take it outside, so this is just F nu nu times L, where L is the length here of the cloud or the slab. Okay. And we're going to write down our free expression, which was what exactly? 3.7 times 10 to the 8 NE and I T to the minus 1/2 nu to the minus 3, and I'm just gonna take this h nu divided by kT. I've already assumed that this is in the Rayleigh-Jeans tail. That's this. All right. Where was I? Right. Okay, so we of course also know that B nu in the Rayleigh-Jeans tail is just, what is it? Well, it's 2 nu 3 C and then h nu kT, right? So that's just 2 nu k c squared and then nu squared t. Okay. So if we look now at the dependencies, then we see that, let's take our normal. I nu emission in the case that tau nu is much, much greater than 1, well, then we know we don't have any backlit here to worry about. This vanishes, and it's just a reflection of the Planck function, which in the Rayleigh-Jeans tail is just proportional to nu squared. Okay? However, when at some point the cloud becomes optically thin, then we see that this changes, because then this is approximately B nu of t times tau nu, okay? But if we look at the proportionalities here, well, this is nu 2, right? But tau nu, we have just said it's alpha nu times the length, and alpha nu has a dependence in the Rayleigh-Jeans tail that is nu to the minus 2. This we have done, right? So this is nu to the minus 2, so that's just frequency independent. So you have a shift in the emergent intensity spectra when at the frequency now that this becomes optically thin. Okay? So now, does that occur at low or high frequencies? Well, you can see this because the absorption coefficient of Bremsstrahlung has an inverse dependence on frequency. That is that at lower frequencies, it will be higher. So if it's higher and higher at lower frequencies, the optical depth, of course, will also be higher and higher. So at some point in the low frequency end, it will transition to become optically thick. So if we now plot the tentative spectrum of log I nu emergent versus log nu for the Bremsstrahlung, then at low frequencies, it will just be a power law following nu squared. Yeah, this doesn't have any units on it, so it's just a that. Yeah, there. This is just a power law. Tau nu is much, much greater than unity, and this then follows nu squared. So in log, it's just a straight line. However, in the optically thin region, it will at some frequency will become optically thin, and then it will transition to a region here, which is then optically thin, and where the frequency dependence is 0. So the shape of the emergent intensity spectra should be something like this. Now, in the lecture notes, in the course book lecture notes, in chapter 1, we have a spectra from an astrophysical nebula, more specifically the Orion Nebula, which is one of these ionized nebula with an actual observed spectra. It's kind of old, it's from the 70s, but still, it has this exact shape. So by just this analysis, we can understand the spectral shape of that thermal Bremsstrahlung emission from an actual astrophysical observed nebula. In this case, the Orion Nebula. However, we can do even more. We can estimate the mass density of this nebula from only this, what we have learned. So, how do we then do that? What do we need to keep? Probably this. So, we're going to say now that we have a certain situation where in this nebula, we observe the thermal Bremsstrahlung, and that this shift from essentially a power law to a frequency independent, which technically because of the Gaunt factor has some sort of minus 0.1 weak dependence in it, but we neglect that. Yeah, and the nebula is on the order of 10 to the 4 Kelvin. Okay. Now, we observe this knee here at the frequency nu, we can call it nu knee, yeah, of 300 hertz, which if you look in the figure, it's not such a bad estimate. This is nu knee. Yeah. There. And from alternative measurements, that is that we have taken images of this, we have measured its angular diameter or something like that, and then we have gotten that the size of this nebula is 10 parsec. For the Orion, this is a little bit too big for the example, but okay, it's fine. Now, then, where does this transition occur? Well, we know that it's going to occur roughly at optical depth unity, because that's the transition between optically thin and optically thick. Again, this is not exactly right. For that, you need a detailed radiative transfer model, but you can get a good estimate from it. So let's say that this occurs exactly at tau nu equals to unity. Well, then we just have this, and we set this to unity. So 3.7 times 10 to the 8 NE NI t to the minus 1/2 nu minus 3, and then
Rayleigh jeans times the length, and that's unity, okay? So now we assume, we do our standard assumption in the course, we live in a hydrogen universe, and since we have 10,000 Kelvin, we have an ionized nebula. That's sort of the onset. That's why we have Bremsstrahlung, by the way. So then we know that the number of electrons has to be equal to the number of ions, because it's just the number of protons, right? Yeah? Voila. And then we can just solve for NE squared directly. And it's going to be, yeah, what's it going to be like, really? Well, we're going to have, this is -3, so we're going to have T 3 1/2, right? And then we have a nu -2, so nu ni, yeah, whatever that was, 2, right? And we're going to have a K coming up here, and there we're going to have 3.7 times 10 to the 8, and I might have forgotten something, okay? But you can go back and track this. And then, as you can see, we have an L, of course. We need the length. And of course, then you have to keep your units in order. I gave you this in parsec. I gave you this in hertz. I gave you this in some other units, so you have to make that interactive when you do a numerical example. Yes, please? Sorry? Ni. I called it age ni. I could have called it age, new ni, not age. New ni. And the age is supposed to be somewhere, right? In the denominator. Thank you. All right. Now, if you plug in these values, you will get that the electron density is on the order of 400 per cubic centimeters, which is just a tiny bit low for the Orion Nebula, but not a bad estimate at all. And the reason why it's a little bit low here is that I assume there was 10 parsec. Yeah, you should really, for the emitting area of this, I should take it a little bit lower. Huh? Now, okay, often what we want to do is that we want to think in mass densities. That's what we do in our course, right? So here, yeah, the mass density in our hydrogen nebula, right, is just going to be the number of protons, the mass of the protons, plus the number of electrons, the mass of the electrons. But these are just the same, so number and that's just the hydrogen atom, right? So that's then just 400 times, what is it, 1.7 times 10 to the minus 24 grams. So on the order of 10 to the minus 21 grams per cubic centimeters. And that's the typical density of your ionized nebula in the interstellar medium. So just by this, looking at the Bremsstrahlung, free emission, we managed to, in 45 minutes now, estimate the mass density of an astrophysical nebula, which, you know, is not such a bad days of work, I would say. Now, before I leave you, I just wanted to make some remarks, because we have done these type of estimates now in several situations, so we can do this. I mean, okay, so this is a nebula, right? We can also do this in other situations and call it some sort of typical for the interstellar medium. That is the medium that is in between the galaxies, right? So say that this typical nebula or interstellar medium is then on the order of grams per cubic centimeters. All right. Now, remember, we did for the universe at large today, that was on the order of 10 to the minus 31 grams per centimeter cubed. Yeah? We have also done for stellar atmospheres, where we had a typical 10 to the minus 10 grams per cubic centimeters. And of course, we have our typical benchmark, which is the air in this room, which is on the order of 10 to the minus 3 grams per cubic centimeters. Remember that, in a sense, I already used this when we took the interstellar medium and estimated how long time it took between collisions of atoms in that. And this is another reflection of just how rarefied this is and how frequent the atoms or the molecules in the room collided. You can go back to that and view to see, you know. I mean, the timescales are just immensely different. And if I'm going to be honest, yes, we can do this calculation. And just by this, and we looked at the spectra, we didn't look at it now, but we have it, and we put it, we will look at it, of course. And then we could estimate the mass density of the astrophysical nebula from its Bremsstrahlung just by learning about these basic physical principles. Now, on the other hand, I cannot say that I really understand what it means to have a mass density of 10 to the minus 21, which is like 18 orders of magnitudes lower than the mass density in this room. That is 18 orders. It's not a factor of 18, it's 18 orders of magnitudes. So, and similarly, when we go to the universe as large, it's like 10 to the minus 31. Or if we like in the spring, for those of you in the master's course, when we consider galaxy clusters and the typical mass densities in there, which are even smaller, right? Now, despite that, we started with saying we have the observations. So the mass densities are so low, but even so, we see it. Using our telescopes, we see this thermal Bremsstrahlung. Just as we see the gas in between individual galaxies in clusters of galaxies, despite the fact that it's so tenuous. As compared to anything, really anything, that we will ever experience in our daily life. And as you can see in just this course, yeah, we do span some 30 orders of magnitudes in our various estimates that we do of this from different situations. And yeah, it's always nice to take a second to consider that fact, I think. All right, that's it for today. That was our Bremsstrahlung.